network in conditioned fear explores the neural dynamics of fear conditioning, specifically focusing on the amygdala and the salience network, which includes dorsal anterior cingulate cortex (DAC) and insula during classical fear conditioning using fMRI. The authors aim to investigate the decline in amygdala activity during fear acquisition and the corresponding changes in salience network activity over time. So the key findings were amygdala adaptation. Over the course of conditioning, the amygdala showed attenuated bold or blood oxygen level dependent response in later trials, suggesting neurobiological adaptation. This is consistent with the hypothesis that the amygdala is primarily involved in the initial stages of fear acquisition, encoding associative novelty, but its role diminishes over time as the association between conditioned stimulus CS and unconditioned stimulus is learned. Salience network dynamics. The insula and DACC showed similar patterns of decreasing activation over time, reflecting network level adaptation. Representational similarity analysis RSA indicated that over repeated exposures, the differentiation between CS plus conditioned stimulus paired with CS with the US and CS conditioned stimulus never paired with US. Oh, okay. Differentiation between CS plus the conditioned stimulus paired with the US and CS minus conditioned stimulus never paired with the US became less pronounced in both the amygdala and the salience network, reflecting a decrease in the neural distinctiveness of these stimuli. Functional connectivity, the adaptation of the amygdala, DAC, and insula was coordinated over time, suggesting that these regions adapt in concern as part of a broader network. The decline in bold responses and representational dissimilarity were linked, supporting the idea of a large-scale reconfiguration of brain areas involved in threat processing as the organism learns the CS-US contingencies. Now, decline in amygdala activity during fear acquisition. The amygdala primarily encodes associative novelty. Once contingencies are learned, its role diminishes, leading to decreased activity, is correct. So the study suggests that the amygdala's role diminishes once the CS-US contingency is established, which fits the idea that amygdala primarily encodes novelty in associative learning process. As the CS becomes less surprising, no longer novel, its activity decreases, which is also evident from the study. And C, the pre-exposure to conditioned stimulus CS during the habituation phase resulted in latent inhibition, reducing subsequent amygdala responsiveness. So the habituation phase in the study involved pre-exposure to both CS plus and CS minus, which likely led to latent inhibition, a phenomenon where repeated exposure to a neutral stimulus without reinforcement makes it harder for that stimulus to later acquire a conditioned response. This could explain some of the reduced amygdala responsiveness observed. Now D part, decreasing BOLD, bold response in the amygdala reflects a reduction in orienting and attentional engagement with CS plus as the stimulus becomes less salient over repeated exposures, leading to a more efficient allocation of neural resources. Okay, so explanation, the decline in amygdala activity can be understood as a shift from initial attention and orientation to CS plus towards a more efficient neural response as the stimulus becomes familiar. Over repeated exposures, the stimulus salience decreases, the importance of the stimulus increases, and the brain allocates resources to more relevant stimuli or behaviors. Alright. Now, methodological design. The inclusion of a habituation block in the current study helped reduce the impact of latent inhibition by facilitating more rapid conditioning. The habituation block was essential in reducing latent inhibition. It allowed participants to become familiar with the stimuli before they were paired with the aversive unconditioned stimulus, helping facilitate faster and more effective conditioning during the acquisition phase. Now, the acquisition phase included 120 trials in which all CS plus trials were paired on a probabilistic schedule, 25% reinforcement rate, allowing study to investigate trial-by-trial adaptation effects. So the probabilistic reinforcement, 25% CS plus trials paired with the US, in the acquisition block provided the opportunity to examine trial-by-trial neural dynamics and allowed for analysis of adaptation in response to conditioning. The study used Gabor patches, oriented grayscale gratings as CS plus and CS minus to control for low-level perceptual confounds, minimizing the influence of complex semantic associations on fear learning. Explanation, the Gabor patches, which are simple grating stimuli, were used to control for perceptual confounds, ensuring that the study focused on basic sensory processing of the stimuli rather than complex semantic associations, which could have introduced variability in the results. Now, CS paired trials were excluded from the analysis of CS activation due to concerns that US evoked activity could contaminate the observed neural responses. CS plus trials where the CS plus was paired with US were excluded from the analysis because US related activation, example loud screen, could interfere with the neural responses to the CS plus, which would have confounded results.